Chapter 1 Introduction to Simulation, Part 1. Let's have the first definition of our course, which is systems. So, when we talk about a system, we mean a collection of entities, right? A collection of entities. Entities could be in type of people, factory orders, cars, phone calls, data packets, and so on, which interact to accomplish some logical purpose. Okay, so yeah, usually a system is a set of entities that these entities interact with each other in order to accomplish some logical purpose, the purpose of that system, right? So in simulation systems, when we talk about entities, we will see later on in this chapter that what's the definition for entities. So we will have a specific definition for entities, which we mean in a simulation. So yeah, in simulation systems, we will have different types of entities like people, factory orders, for example, cars, and so on. So these entities will interact each other and work with each other in order to accomplish some logical purpose for that system. Okay, so the examples here we can say banks, customer, teller system, right? So in the bank's customer teller system, we have entities in type of people, which are customers or clients, and the teller or the server, right? So customers will come to bank for some requests for some transactions, and they may line up in a line, and then when after waiting in line, they will have their request to the teller, and teller will process their request, and at the end customers will leave actually the bank, right? So this is a system, and if we are going to simulate this system, we need to consider the entities in the system, right? Or a simple machine processing system, like in this diagram, you see that the blank parts. So this is one of the entities in the system, right? These entities, I mean, the parts will arrive the system. They will be in a queue or line based on with the logic of first in, first out, and then the machine will process the parts, and then the finished parts, I mean the processed parts, will depart the system, right? So this is a simple machine processing system, right? Or flexible assembly system in a factory, warehouse, logistic network, economic system, or local area network. All of these ones are examples for the systems, right? That which we mean in this course, or in general definition for system. So a system may be contained with another system. So yeah, we have different type of systems in different levels. So at any level, a system may be a subsystem of a larger system, right? For example, the customer teller system will be a subsystem for the bank system, and the bank system could be a subsystem for the Canadian economy system, right? And then the Canadian economy system is a subsystem of a global economic system, right? So as you see, in different levels, we have different definitions. I mean, any system in any level could be a subsystem of a larger system in the higher level. Okay. So what do you mean by analysis, improvement, or design a system? When we have systems, so we need to study the systems, right? So why we need to study the systems? Because we need to measure the performance of the system. And then based on the measured performance, we may need to do some actions to improve the performance of the system, right? And then we may need to design a new system. We don't have a new system. We need to a new system, but it's not existed, so we need to design that system based on the needs that we observe. And in any system, we need to control the operations and the process of the system, right? So because of all these needs, I can say we need to study a system, right? So how can we study a system? We may play with the actual system, right? That's one option. We can do all the ideas that we have in our mind as changes to the system. We can apply them in the real system to see what are the impacts on the performance, right? The advantage of this option is unquestionably looking at the right thing. Yeah, because we don't build a model in this approach, so we are trying all the ideas, all the changes that we have in our mind in the actual and real system, right? So that's good because we will observe all the right things. Okay, so example, adding one more station in drive-through service, right? So let's say we have a drive-through service right now, but we see that most of the time we have a line, and the waiting time for the customers is somehow a considerable number, right? So we are thinking about adding one more station for the drive-through in order to levelize the waiting time and balance it and decrease the waiting time for customers. Okay, so yeah, in this case we may just add one more station and see what will happen in a week or in a month, and after a week or after a month we will have the performance, and in that time we will see if it's necessary to keep this new station or we don't need it and we can eliminate it from the system, right? So that's the approach that we try the changes in the real system. But in many times, it's impossible to play with the real and actual system because it's expensive, because it's not doable in technical aspects, like, or because it's not safe to implement the changes that we have no idea about their impact in other systems or other aspects, right? So all of these issues, in many times we need to build a model of the system and then try the changes, try the ideas that we have in our mind on a model before applying them in the real system, right? So yeah, this is why we need a model for a system, because it could be disruptive, it could be expensive, or it could be dangerous, right? So in these cases, we need a model. So we have to build a model of the real system, and then we will work on the model. We will try all the changes that we have in our mind, all the ideas that we have in our mind on a model, and then we will have the results, or we can gain insights from the model, and then based on that insight we can finalize our decision on the changes and the improvements and the ideas, and then we'll apply that option in the real system. Okay, so what's the definition of a model? A model is a representation of an object or a system or an idea in some form other than that of the entity itself. So this is the Shannon's definition for a model. So usually for building a model, we need to consider some sort of assumptions and approximations about how the system works. So yeah, a model is a simplified version of the actual and real system, right? So we need to consider some sort of simplifying assumptions and approximations. And so, yeah, by having a model, studying a model instead of the real system is usually much easier, faster, cheaper, and safer. Okay, can try wide-ranging ideas with models. So, yeah, make your mistakes on the computer, not actual system, right? Yeah, and often just building a model is instructive regardless of results. So if you don't have any uh, surprising results from a simulation model, that's okay, because just building a model, it could be instructive by itself. Okay. And so by having a model at the end, we need to verify and validate of the model. So it's for all kinds of models, not just for simulation. So without validation, we can't actually rely on the results obtained by the model. So in order to be uh, uh, actually confident on the results, so we need to verify and validate the model at first to make sure that it's a good representative of the real system, and then we can rely on the results and data obtained by the model. Okay. So in general, we can have two types of models, physical or iconic, and logical or mathematical models. So physical models like prototype plans or tabletop material handling models. So yeah, they are physical, they are built in small scale of a real system, right? The logical or mathematical models that we are going to use in this course are based on some approximations, assumptions about the system's operation, and usually we actually represent the system by some equations, mathematical formulations, and at the end by a computer program, okay, in appropriate software. And then we can exercise the program to try different things, I mean changes or ideas, and then get results and learn about model behavior. And then based on this learning, we'll have insight about the real system. And then based on that insight, we can make our decision on the new system or the changes that we are going to have on existing system. Okay. So here we'll see the approach to study a system. Uh, we can study the system by trying or playing with the actual system, or we can experiment with a model of the system. So if the system is simple enough and trying different things or changes in the real system is not expensive, it's not dangerous, and it's doable and applicable. So yeah, I mean, we can try with the real system without having a model. But if the system is complex and it takes time, it's expensive, it's not safe to implement the changes that we have in our mind without having a clear investigation on the impact of the changes in the real system. In that case, we need to have a model. Okay, so a model could be a physical model or a mathematical model, and in this course we will actually work on the mathematical models. So the simulation models are the category of the mathematical models. Okay, and a mathematical model could be an analytical solution, a model to have analytical solution, or it could be a simulation model. So when we talk about the analytical models, we mean the prescriptive modeling. In prescriptive modeling, we will have a mathematical model that will give us an optimal solution, and we can apply that optimal solution in the real system. Like the linear programming in the operation research course, you had the linear programming model or integer programming model. Those models are examples for the prescriptive modeling, which are in the category of the analytical solutions, right? So if the system, the real system is not too complex, and you are able to formulate the behavior and the operation and the process of the system by some sort of mathematical equations, then we can formulate the system by a mathematical model which can be solved for the analytical solution, for optimal solution. So these are the prescriptive models. But if the system is too complex and we are not able to formulate the actual behavior of the system with mathematical equations, and we may need to consider some sort of logical relationships or some sort of descriptions and algorithms and flowcharts for the system, which cannot be formulated by mathematical equations. In that case, we cannot actually use the analytical solution models. So in that case, we need to consider other approaches like heuristic models, or I mean, if you're not able to use the analytical models, it doesn't mean that you need to apply a simulation model. You can consider some sort of heuristic methods, right? Again, if it's not possible and the system again is more complex than the system that we can apply a heuristic method, then in that case we may need to use a simulation model. Okay, so the simulation models will be used for two complex systems, and they are in the category of descriptive modeling. So descriptive modeling are the models that they will not prescribe uh, prescribe an optimal solution, an analytical solution for the system. They will describe the behavior and the performance of the system. Based on that description, we can find out what kind of changes or what kind of solution could be appropriate for the system. Okay, so this is why we call these models as descriptive modeling. Okay. So what's a simulation? Simulation is an imitation of a real world process or operation of the system over time. So this is uh, the official definition for simulation. So in simulation, we generate artificial history for the system, right? Since we have a model, that model is a representative of the real system, then we run that simulation model to generate data. So since they are based on this simulation, so we call them as artificial history of the system, right? And then based on this artificial history, we analyze the behavior and performance of the system, and then based on this analysis, we can make our inferences about the real system. Okay, so this is how a simulation model works. Okay, so let's see when and how we can use a simulation model. After building a simulation model and verifying and validating it, then we can use that simulation model to answer the what if questions. You may have a lot of questions in your mind that what if we change this part of the system? What if we do this? What if we replace this? And so on. So we can answer all these what if questions in the simulation model instead of the real system. Okay. So if we have an existing system and we would like to make some improvements in the performance of their existing system, and so by having some changes in the system. So in this case, we are saying that the distribution model is used as an analysis tool for the current system. So yeah, as analysis tool, you can implement your ideas in the simulation model, and you can predict the effect of the changes in the real system based on the simulation data. So in this sense, it's called analysis tool. Okay, or if there is no current system and we're going to design a new system, and we have different scenarios or options that we can consider in the new system, and we don't know which scenario and which option will be better in terms of the performance. So in this case, we build a simulation model. We try all the scenarios and options in the simulation model, and based on that, we can predict the performance of the system, the new system, I mean, based on all those conditions and scenarios and options, and then we will finalize our design with a specific scenario and option for the new system. So in this case, we say that the simulation model is used as a design tool. Okay, so as you see here, the simulation model can be used for analysis, can be used for design, and can answer all the what if questions. Okay, we usually have randomness in the systems that we build a simulation model for that system. So yeah, we can actually incorporate randomness in the model, I mean in the simulation model, and then we can describe the randomness with a probability distribution. So yeah, we need to consider probability distributions for some parts of the model in order to contribute or consider the randomness. So in this course, we'll learn how we can fit a distribution, a probability distribution for that part in the system. Okay, and yeah, we will generate random numbers or random events based on those probability distributions, and we make simulation as experimenting on a computer instead of experimenting in the real system. Okay, so let's see when simulation is not appropriate. Okay, so when the problem can be solved by common sense, so the system is simple enough and can be solved by common sense. So in this case, we don't need to have simulation. Or again, the system is simple enough and we can solve it analytically by the prescriptive models. Again, in this case, we shouldn't consider simulation. And or performing direct experiment on system is less expensive. Yeah, trying the actual system is less expensive and it's doable. So yeah, in that case, again, we don't need simulation models. Or if the costs of simulation exceed the savings. Okay, and if the resources or time are not available, so when we talk about the resources, we mean budget, time, data. So if you don't have data about the history of the system, so we can't build actually a simulation model, because we usually fit the probability distributions based on the historical data. So if you don't have data from the history of the system, so how we are going to build I mean the probability distributions and then simulation model. Or if we don't have much time in order to build a model, so we can't use simulation, or if we don't have enough budget, again, we are not able to apply simulation. Okay, and if system is too complex or cannot be defined, like human behavior, yeah, if system is much more complex, in that case we cannot even apply simulation, because we can't simulate the human behavior, for example. So how we are going to build a simulation model for human behavior? There is no sense, there is no knowledge about the human behavior, so it's not applicable, right? So these are the cases or condition or case, I mean, the situations that we cannot use a simulation. And other than that, if we actually see other conditions are in place, then we can apply a simulation model. So that's the first part. I mean, the first part of the introduction to the basic terms and concepts in simulation. So we will see more concepts and definitions in the rest of the parts of this chapter. Okay, thank you.